I'll complete our discussion of Chapter 12 with a few minor topics, the first of which is a supercritical fluid. If you have a liquid in a vessel that can contain high pressures, then that liquid will exist with its vapor pressure above it. So we have a liquid and gas in a high pressure container. As we begin to heat that liquid, then the liquid may begin to boil, and the meniscus, or the line between the liquid and gas, begins to blur to the point that we get what's called a supercritical fluid. And that's the point at which, no matter how much pressure we add, we cannot condense the liquid back into its liquid state. We can't condense that substance back into its liquid state. Sublimation and deposition are opposite processes. The process of sublimation occurs when a solid enters the gas phase without going through a liquid phase. The opposite of that process would be deposition. So even molecular solids have a vapor pressure. Substances can go from the solid to the gas phase directly. This happens, for example, with carbon dioxide, dry ice. If you have a chunk of dry ice, it will go from a solid directly to a gas. And the gas would be carbon dioxide gas. This is why you don't want to store dry ice in your car with the windows up. So if you're carrying dry ice in your car because you want to carry maybe some frozen goods from one location to another, and dry ice is an excellent way to do that, you want to make sure that you have a window cracked so that you can get oxygen and so that you would not be asphyxiated during that trip. So this is just an example of what sublimation is, going from a solid to a gas phase without entering a liquid phase. And here's an example of how that would happen. So water can also sublime. You may have noticed this if you live in a colder area. So snow can, instead of melting, if even below the freezing point of water, even below zero, if the temperature remains below zero, snow will eventually dissipate, and it dissipates through the process of sublimation, going straight from the solid to the gas phase. And this is because it may have enough energy to go from solid to gas phase. Maybe with the wind blowing over it can give some of these molecules enough energy to enter the gas phase without going through the liquid phase. If we look at a supercritical fluid on a phase diagram, we see that the supercritical fluid exists somewhere above the point at which the substance would be able to transition from a gas to a liquid or a liquid to a gas. And on a phase diagram, that is called the critical point. So here we see the phase diagram for water. Phase diagrams describe the different states and the state changes that occur at various temperatures and pressures for different substances. Okay, so we can see here the liquid gas line is our vaporization curve. Okay, the fusion curve is defined by the line between the solid and the liquid state. And the sublimation curve is defined by the line between the solid and the gas state. Sublimation is the transition from a solid to a gas without going through the liquid state. We see here the triple point for the substance, and the triple point is where the substance exists in the solid, liquid, and gas states all at the same time. So this is a phase diagram for water, and here we have temperature on the x-axis and pressure on the y-axis. So you can see here that maybe at 760 torr, that's atmospheric pressure, if we're less than 0 degrees C, we have ice, right? We have the solid phase. As we transition to the right, at atmospheric pressure, we're increasing the temperature but not changing the pressure. So at 0 degrees C, the ice will transition from a solid to a liquid when we reach the fusion curve. As we increase the temperature further, we are heating the liquid water. At 100 degrees C, we're going to reach the vaporization curve for water, and the water will transition from a liquid to a gas. As we increase the temperature above 100, then our water is all in the gas form. So if you know the pressure and the temperature at any point, you can determine what phase you will have for water from this curve. For example, let's say this is 200 torr. Okay, this is roughly, let's say it's about 200 torr. And let's say we're at 200 torr for the pressure, so that's pretty low pressure, and we're at maybe 25 degrees C. At 200 torr and 25 degrees C, we would be in the gas phase. But if we were at atmospheric pressure at 25 degrees C, we would be in the liquid phase. So from a phase diagram of water, it becomes apparent that we could boil water at normal room temperature by just lowering the pressure. And this is a process that's used frequently in the lab to actually purify substances, that through distillation we can just lower the pressure using a vacuum, and we can cause those substances to boil even at room temperature, and we can purify substances in that way without maybe destroying them. So this is a common technique. We see here some similar phase diagrams for other substances. On the top we have iodine, and you can see iodine also has a triple point, but it's at a different temperature, right? So at 114 degrees C, and a little below atmospheric pressure, we have a triple point for iodine where it exists as a solid, liquid, and gas, but it has a similar phase diagram, but the temperatures and pressures are different. So if we move this way, we can transition across the fusion curve from a solid to a liquid. If we move this way, we can transition from a liquid to a gas. So you can use the phase diagram to determine what phase your substance will be in at some temperature and pressure. So say if you were at 1 atmosphere of pressure, and maybe this is 500, this is 200, maybe this is 300 degrees C for iodine, you would be in the gas phase. Similarly, for carbon dioxide, you can see you can go from a solid directly to a gas for carbon dioxide at atmospheric pressure. So this is why carbon dioxide sublimes at atmospheric pressure. It goes straight from the solid phase to the gas phase. Okay, and this would begin to occur at negative 78.5 degrees C. We see that carbon dioxide also has a critical point. Now, critical point is something that isn't going to be observed under natural conditions. We would need a high pressure vessel to observe that type of phase change. Let's look at conceptual connection 12.10. A substance has a triple point of negative 24.5 degrees C and 225 millimeters of mercury. What's most likely to happen to a solid sample of the substance as it is warmed from negative 35 to 0 and a pressure of 220 millimeters of mercury? So I kind of sketched out a phase diagram here for this theoretical substance, and we see that it has a triple point at negative 24.5 degrees C, or about negative 25 degrees C, and 225 millimeters of mercury. Okay, and so what's most likely to happen to a solid sample as it's warmed from, let's say, negative 35 to 0? Okay, It's going to go across this line. So let's look at what that line would be. Okay. So this would be our sublimation curve. It would be going from solid to gas. Now, that's not water, but all substances have, or a lot of substances have similar phase diagrams here. So you're going to see that it would be going from a solid to a gas. Okay, so the substance would sublime.